Hello everybody, and welcome to another highly compressed technical lecture with extremely difficult to read slides. Today I wanted to talk about a thing called Quaternion double cover, which some of you may know what it is, but almost nobody actually uses it, which is unfortunate because it's kind of a great aspect of quaternions, and hopefully, as you'll see as we go through this lecture, can be useful in a number of ways. So I wanted to kind of cover what it is and why you should care about it and how to use it effectively. When I say double cover, of course, I'm referring to the fact that quaternions, which in games are now very often used to represent orientation or rotational quantities, they actually can represent more than 360 degrees of rotation. They can represent up to 720 degrees of rotation before they are back to what you would consider no rotation at all. So meaning a rotation of 0 degrees and a rotation of 360 degrees in some rotational representations would be the same. But in quaternions it's not the same. It actually remembers the fact that you've gone 360 degrees round if you would like it to. Now, most games and most algorithms that are using quaternions today in games, they do not take advantage of the fact that you can represent the 720 degrees of rotation. Very rarely is there anything that actually uses this. But it turns out you can actually do a lot of really nice things with this just by making some slight changes to the way that you do your quaternion operations. You can get a lot of really positive benefits, and that's what I'm going to talk about today. This is not meant to be an introduction to quaternions. I'm just going to assume that you know how quaternions work and that you're very comfortable with them. If you're not, then I apologize, but I just don't have it in me to do a full introduction to quaternions today. Maybe someday we could do that, but not today. So, quaternion double cover. First of all, let me just say that apparently, if you're a physicist, and I'm not, the concept that there are only 360 degrees of rotation is not actually a given. Apparently in the physical world with, I don't know, quantum particles or God knows what, there actually is a concept that nature itself distinguishes between 360 degree rotations and 0 degree rotations. And apparently it's only once you get to 720 degrees of rotation that everything is back to the way that it was, and it actually is truly the same. Now, I don't really know the specifics of this because I'm not a physicist, but apparently it has to do with the fact that if you considered the fact that something that was going to rotate had sort of tethers attached to it, or two strings attached to it on either side, let's say, and then you spun it around 360 degrees in any direction, those strings would be wound. And apparently, if you rotate 360 degrees, there is no way to untangle the strings to make them back to their neutral state. But I guess if you rotate 720 degrees, you can actually do it. Now, I have no idea because I don't know the physics of it, but if you're interested in kind of the sort of weird 720 degrees might be the right amount of degrees to track thing, definitely Google on that, read more about it, and hey, maybe post on the Molly Rocket forums and tell me why, because I have no idea. Charles Bloom, I don't know if you go to www.cbloom.com and send him an email, he also knows how to do this crazy belt trick. He went to Caltech, so of course he knows all the physics things, and I think he can do this crazy belt trick that demonstrates why. So maybe if we're lucky, Charles will someday do a little belt trick video for us, and we can put that up on the forums, and maybe you can get a better idea of it. But anyway, the point is, 720 degrees in the real world might not actually be the wrong number of degrees to track. So I say if it's not wrong in the real world, maybe it's not wrong in the game world either. And hopefully you'll agree with me at the end of the lecture. Now, quaternions, they track 720 degrees of rotation, which means that when you go through 720 degrees, you're back at the same quaternion that you were at originally. But if you go through 360 degrees, no matter what axis you pick, you always end up with a different quaternion than if you had just stayed where you were, which is not the same as, say, if you did that with, maybe another thing like a matrix representation of the rotation. So why is that, and what actually happens there? Well, what happens is, if you look at the construction for a quaternion, I've just written it out in angle axis form, essentially, which is to say that I'm going to construct a quaternion that's taking a vector v and it's rotating theta degrees about that axis. What I get is the three components of my, the ijk components, if you will, of my quaternion are going to be that vector, that angle, the axis of rotation, times the sine of half the angle. And then the fourth component, or the w component, or whatever you want to call these, is going to be the cosine of half the angle. Now, you can immediately see where the double cover comes from, just from looking at this. The fact that the angle is divided by 2. Now, we all know sine and cosine, they're periodic functions, right? But they're periodic on 360 degrees. So if this was just sine theta and cosine theta, then quaternions would only be representing 360 degrees of rotation. But because it's divided by 2, you have to go twice as far, or 720 degrees, in order to get sine to go 360 degrees, which is where it will be periodic. So as a result, our quaternions have built into them the fact that we can go 360 degrees and be at a different quaternion. Now, what quaternion will we actually be at? Well, many of you already know the answer to this, but just for clarity's sake, if I assume for ease of discussion that I'm going to rotate about the same axis, and I'm going to rotate 0 degrees, 360 degrees, and 720 degrees, respectively, then what I'm going to get is my cosine term, if I'm rotating 0 degrees, is going to be 1, because, hey, cosine of 0 over 2 is, of course, 1. And then if I'm going to rotate 360 degrees, then normally if I was rotating cosine of theta, right, I'd be all the way back to where I was, and it would be 1 again, but I'm not. Because I'm only rotating theta over 2, which is 180 degrees, which means I've gone to the other side of my circle and I'm at -1. So I have to go to the full 720 degrees before I get back to 1 again. Now, as you can see from this, just from this example, I go from 1 to -1 to 1. The difference in the quaternions when I do my 360 degree rotation from where I started is I negate the quaternion, right? All the values are the negatives of what they would be. And that's not just the case in this simple example where the first 3 are 0, because, hey, the sine of theta over 2 is 0 in all these cases. That's not just the case there, it's the case anywhere, because as you can see, the angle, if we assume that the angle of, the axis of rotation is not changing, then the only thing that's changing is the sine and cosine terms. And we know that the sine of theta is equal to the negative sine of theta plus 180, and same with cosine. So whenever we go 360 degrees, we're going 180 degrees in sine and cosine land, which means we're going to negate these two values, which means exactly as we said before. Okay, so now, just to underscore this point, here is my magical circle, here is sine, here is cosine for some angle theta, right? If I go 180 degrees around, I still get the exact same triangle, right? My cosine is exactly the same, my sine is the same, it's just they're going in a different direction. And that's basically all we're seeing here. So our quaternions, as a result, are going to be the negative of whatever they were if we go 360 degrees. And then they're going to come back to what they were originally if we go 720 degrees. Which is why you would often see it's stated whatever, that a quaternion is the same as its negative. There's two versions of it. The quaternion and negative of a quaternion represent the same rotation. Well, they don't really represent the same rotation, right? But they represent the same rotation in 3D. So if we're only looking at the ending 3D position of the object. But really, one of them represents an additional 360 degrees of rotation there, and we're kind of leaving that part out. But anyway, that's the crucial thing to understand. So now, what I'm going to talk about is the Quaternion neighborhood operator, which is to say that sometimes we want to be able to talk about rotations as if they were just their 3D orientation analogs, meaning that even if I'm talking about an additional 360 degrees rotation as far as the quaternion is concerned, I really just want to talk about what rotation that actually represents in 3D if I assume only 360 degrees of total rotation. So the quaternion neighborhood operator is what you normally see to do this, right? Normally you have something where you are going to add things together, like for example, if I'm going to produce a final animation by weighting some, by taking the weighted sum of some animations here, I've got weight 1 times animation 1 plus weight 2 times animation 2 and so on. Then somewhere, when I'm actually computing this, I have to be able to do that operation with my quaternions. I have to be able to do one weighted quaternion plus another weighted quaternion and so on. But when I'm doing that, right, what most people go is, well, sometimes I end up with the negative quaternion, and sometimes I end up with the positive quaternion. What I need to be able to do is when I'm blending, I need to make sure that no matter whether it was the quaternion or its negative, I always use the one that is closest together to whoever I'm blending with. because I don't want my animations to go through an extra 360 degrees when I blend them together. I don't want that kind of effect. So what we do is we use this little quaternion neighborhood operator, which is the dot product of one of the quaternions with the other quaternion. If that's less than 0, then that means that one of the quaternions was on the other side of the 4D hemisphere, right? One of the quaternions was essentially the negative of what we'd actually like it to be. So all we do is we invert the weight that we were going to use for that quaternion, and then we can add them together. Because essentially we can take any quaternion, we can use its negative, and get the exact same rotational quality in 3D, meaning the exact same final rotation, only this time it won't have that extra 360 degrees of winding. I'm not going too deep. I hope you understand this because I'm just kind of covering what I assume people are already doing. So that's why I'm not going too much into detail here. Again, if I'm going through this too fast, please feel free to go to mollyrocket.com/forums where this video is posted in the dev notes, the tech notes forum. Go ahead and just post questions in there, and I'm happy to answer them. But I'm assuming that you already know all this stuff. Okay. So what we're doing here is we're always performing this, what I'm calling the neighborhood operation. We're always going, if these two quaternions are further apart than 360 degrees, map one of them into side the 360 degrees and just do the blend there. So that's what everyone is currently doing, and that's what most people normally do, and that's okay and that's fine, and obviously it works great and all that. But the question is, are we losing something there? Are we losing some properties that we might want to keep by always forcing things to go through this kind of neighborhood operation? I should also mention as an aside that if you're not comfortable with adding quaternions together, you should be. I've been trying to advocate that people cannot add quaternions together for a very long time, and John Blow has written articles about it in Game Developer Magazine. You can go to number-none.com and read. I think he's got an article there on quaternions. Anyway, go to the Molly Rocket forums and I'll post a link to it. If you're not comfortable adding quaternions, you should be. So, definitely go become comfortable with it before we go any further, because that's underlying this entire thing. Okay. No slurp. We're not talking about slurping here. Slurping bad, don't slurp, only lerp, only add, adding good. Okay, there you go. So continuing along, I'm going to talk about what the properties are that we might be losing here, that I was kind of alluding to previously. So suppose I have one animation, and it's got, this is my awesome bone structure of a guy. Do you like it? I know, it's very artistic. So suppose I have one animation of a guy, and I'm blending two animations together, this one and this one I'm going to blend together to get a third animation that I'm trying to create the blended version of. And I need to blend together this kind of arm position with this kind of arm position. Now, if you look at it, it's kind of the guy's got his arm back like this, right? And then he's going to blend to having it up like this. Now, you know that I can't do that, right? I can't get my arm to go up there because, hey, that would be ridiculous. Our arms aren't built to do that. That's not an acceptable rotational movement, right? But unfortunately, when we talk about the quaternion neighborhood operator, if we take these two orientations here, the closest way to go, even though the desired thing to do is to come all the way around here, right, to kind of come around this way, because that's the way the human arm works. Unfortunately, the actual thing it's going to do is just pick this really short distance here, right? It's going to do the unnatural thing and just kind of torque that right up there because that's the shortest thing. And that's what you've told the quaternion to do, right? You told it to go the shortest distance because you put the two things into the neighborhood together so that they would blend closest, right? But that's really not what you really wanted, right? So maybe now you can think, what could I do, right, that would allow me to sort of automatically not do kind of obviously bad things like that without having to put in weird stuff like joint constraints and all, kinds of things checking and going on in there in the middle of the blending and that kind of stuff. And, since this is since this video is about quaternion double cover, you might think to yourself, well, hey, could I use quaternion double cover? And yes, you can. If, for example, I knew, right, what the general neighborhood should be in which all of my arms operations should be blended, if I knew what that was, then I would always just do my operations in that neighborhood, right? Instead of doing it in whatever neighborhood the two quaternions are closest in. I do it in that neighborhood, And then I would never pick a rotation. If I had a rotation like this and a rotation like this, those two things both represent that and that, respectively, right? So it's like, this is one, and this is another. They would never think they could go like this, because really there's a hidden 360 degrees they'd have to go through in there to get from one to the other, right? Because if I start here and rotate here, and I start here and rotate here, right? If I'm starting and doing these two rotations, then even though it may be shorter when I don't have a full 720 degrees to go through, even though it may be shorter to looks like it could go like this, there's that hidden extra 720 degrees in there, right? And if we use that, if we place that hidden 720 degrees at just the right place, then those guys won't go through it, right? They won't be able to go through it because it's way shorter to just do this long rotation, even though it looks longer than this, right? This thing, than this, the thing I can't do, even though it looks shorter than that, it's not, because there's that extra 360 degrees in there, right? That's the double cover area. So, if we could just have our artists go ahead and manually place their double cover all over the place, right, this would just totally work. But chances are you probably don't want to have your artist watch this video, because my explanations are typically so bad that programmers don't even necessarily know what I'm talking about, so artists certainly aren't going to know what I'm talking about. But what if your artists were already secretly doing this? Like, they all know about the Quaternion double cover, and you are the ones who don't know about the Quaternion, and all you need to do is go look up the special secret all information, double cover information that they put into your art assets, and then you could magically just have it. Well, it turns out, even though I'm making it sound cooler than it is, that they actually already do that. And that's one of the coolest parts about Quaternion double cover. And that is that artists always supply a rest pose for everything. In fact, skinned models don't really work without a rest pose. You need to have the rest pose of the model if you're going to be doing anything with it for the most part in your game. So typically your game engine always has the rest pose of the model lying around in a modern game engine, and it can operate on that. Now, the cool thing about the rest pose for the model is it's all the double cover information that we need. You know that all of the joints in a rest pose model are going to be pointing roughly in a direction that is the neutral pose for that joint, right? Sometimes it's not, I mean, it's hard to say what a neutral pose is, but you know that it's going to be in a direction that is at least comfortable for the model. So if you just consider that to be the basis of the neighborhood for your Quaternion operations, now you know that the double cover is always placed in an area that is sort of opposed to the neutral pose. And that's all we needed, right? All we need to do is to put that 360 degrees somewhere where we don't want it to go back through, and that's exactly what the rest pose does for us. If we look at any one of our joints, that hidden 360 degrees is basically just right behind it, right? It's where it would have to go 360 degrees back to get to. That's where the hidden 360 degrees comes in, right? So beautiful. Our artists have been doing this all along. We have the information that we need. You can drop this into an existing game engine, and it just magically works. Okay. So assuming that we have that, how do we actually implement something that takes advantage of this, right? Well, it turns out that that's pretty simple too. All we have to do from now on is when we're going to do our Quaternion blending operations, instead of just always applying the Quaternion neighborhood operator, we instead have a mode of combination for each thing that we remember, and when we go to blend a particular animation, or I shouldn't say a particular animation, a particular track of an animation, a particular Quaternion curve, or whatever it is that's generating our Quaternions. When we go to blend each individual track, that track just has, for the whole track, a specific sort of flag that says, or rather mode value that says, how is this track supposed to be blended? Now, there's three ways that we might want to blend it, typically, and these are the three that I use. Technically, you could maybe do more than this, but for now, I'm just going to talk about these three. And they are neighborhooded, inverted, and direct. Those are the three ways that you can blend together. And as you might expect, neighborhood is the way we have been doing it, right? It's always checking to see if they're in the locus and then going ahead and doing it. Inverted is to do the negative. So instead of checking the Quaternion neighborhood and negating based on that, you just always negate. And the other one is direct, which is you just sum it right in. Now, there is one difference with the neighborhood thing, and I'm going to talk about that in a second, which is basically we're no longer going to neighborhood with the thing we're blending with, which is what most people are doing. Instead, we're going to neighborhood with the rest pose. And that's very key, because like I talked about before, we want everything in the neighborhood of the rest pose, because that's our canonical neighborhood. We don't care what the current values are that we're using when we're blending. We always want to neighborhood everything into that neighborhood. Okay. So when we look at an animation, how do we determine, just from the animation data, which one of these modes we should use? Well, it turns out you can get a guess that's right 99.999% of the time. In fact, most games it's right all the time, but you can have situations where it's not quite right to guess this way. So as you can see, I put a star here, which says manual override here, which is to say that sometimes you might want to allow an artist in their art tools to mark, and one particular track of animation as this guy needs a specific blending mode, you're not going to be able to detect it correctly. But I've almost never, in fact maybe haven't ever, seen that happen, but it may happen now and again, so be aware of it. But for 99% of animations, this will just work, so you shouldn't even have to really think about it unless occasionally you get a weird case, and then you can always just override just that one. All you have to do is take the very first Quaternion key in the track and do the dot product of that with the last Quaternion key. So you're essentially looking at are the first and last key in the same neighborhood or not, right? So if that's less than 0, then we're going to do neighborhooding. Because what that means is that the first key and the last key are not in the same neighborhood, which means that this animation starts in one neighborhood and ends in another. So we know that it's an animation that kind of goes through neighborhoods. So this is kind of like something like a wheel that spins around or something like this, who knows what's happening. But point being, it's not staying within a single 360-degree area. So it's doing more than one complete revolution over the course of the animation. So what we need to do is we need to treat those neighborhooded, because we have absolutely no idea what they might be doing. They could be doing anything. This is like, dude gets up and does like a couple barrel flips in the air, right? Well, clearly in the middle of the barrel flipping, if he's supposed to go ahead and blend to like standing upright, he shouldn't unwind himself or do anything like that. He should just blend whatever, he should either unwind or wind forward more depending on which one is closest, right? That's what we want for the most natural looking blend result. So anytime we see something that's obviously doing this, we're going to want to do neighborhood. Now, the reason, again, why I say you might need to manual override sometimes is sometimes something could go through multiple neighborhoods. It could spin more than 720 degrees in a single animation. And in that case, this detection won't work, right? Where you're doing like 720-degree loops, or you're doing like 4 loops, whatever, then you might have to do that. And you can make a more complicated detection routine that actually sweeps through all the Quaternions, looking if you ever go out of the neighborhood, and if you go back in, did you go back in the same way, blah, blah, blah. I'm not going to cover that stuff here. This is usually a good enough check for just about everything. But if you really want to get hardcore on it, you can actually do a little more there. Assuming that you don't need to do it neighborhooded, then you check to see, is key 0 already in basically the rest pose? So if key 0 is not in the same neighborhood as the rest pose, then you're going to always want to use inversion blending. Because again, we want everything when we blend it to be in the neighborhood of the rest pose. So we know this guy isn't, so we're going to just negate him every time when we blend him in, right? We're just going to negate him, because we know he's always out of it, right? And we know that he doesn't change neighborhoods, because if we did, we would have already set it to this mode. So finally, if neither of those are true, then we know that he already is, this animation just already is and remains in sort of the neighborhood of the rest pose, so we just blend him direct. So all we need to do is just do this little simple test on all of our tracks. You can do this when you export them. No, well, you probably can't do it when you export them, because if you retarget animations, if you use the same animation on multiple models, you need to check against the rest pose of that model. So you might have to do this at load time. I do it at load time now that I think about it. So you don't want to necessarily do it at export time if you can't guarantee what model you're on. So at load time you do this, but it's very inexpensive. It's 4-element dot product, maybe another 4-element dot product and 2 checks. Not that big a deal. So then, for every track, you have that mode. And when you have that mode, all you have to do is when you go to do your summations, right? When you're going to, and you're just doing like, I'm summing all my guys into my accumulator, I'm summing all my quaternions together weighted to get my final accumulated value, you're going to do something like, the quaternion accumulator plus equals the weight for this key that we're blending in times the quaternion of this key, right? We're going to be doing that operation. All we have to do is, before we do that operation, modify W key, the weight for this key, in the proper way. If we're supposed to be neighborhooding, then we just take the sign of the Quaternion key dot producted with the rest one. So we do the neighborhood operator on the Quaternion key and the rest pose right now, right? And we use that sign to change the weight, either positive or negative, to leave it positive or negative. We flip it one way or the other, right? And what that does is that just says, okay, we know this animation goes through all kinds of neighborhoods. We have no idea where it's going to be. So each frame, we're just going to neighborhood it into the rest pose's neighborhood. Again, not into the neighborhood of the current accumulator value, which is what a lot of people do, but rather just into the neighborhood of the rest pose. And then we're going to blend it. If we're an inversion blender, we just always negate it. We just negate W key. We just always negate the weight we're going to use, because we know that if we negate this quaternion, we're going to be in the rest pose's neighborhood, and that's what we want. And then finally, if we're a direct blender, we just leave W key alone. We don't have to do anything to it. We just use what it actually is. And then we perform the summation as normal. This is all you need to do. It's that simple, right? All you need to do is go from doing the neighborhood operator every time you blend with the thing you're blending with, to instead either doing that neighborhood operator with the rest pose, or doing either a hard-coded invert or no invert at all. Just going from that to this allows all of your blends for any kind of sort of normal joint motion to just work properly, without having to have any joint constraints or any information like that. It allows the animators a lot more freedom to do whatever they want to do there, and the blends just work. They'll never pick kind of weird things. You'll never see a head spin around behind the back of the guy because he blended from this to this, right? Never going to happen, because there's a hidden 360 degrees back there that prevents it from happening, and it won't pick that path. But it also seamlessly handles all the other things you might want to do. Root motion, where the guy is doing his cartwheels, like I said before, spinning wheels, spinning propeller blades, all of these things are still handled cleanly by the system, because you can always set animations to do those revolutions, and the detector will normally just detect which one it should use. But even if the detection fails because the animation is very complicated, it goes through lots of neighborhoods, and it doesn't pick the right thing, you can always override that manually. And the cases where you have to do that are, very, very few. So I really think this is a great way to do it, and I love the fact that quaternions have double cover, because this stuff wouldn't be possible without it, and you would have to do a lot more work. There aren't really any rotation representations that are used in games that have this property besides quaternions. It's really hard to get something with exactly the just the double cover. So it's really easy to do the neighborhood operator. So it's really easy to do closest if we want to, but also really easy to not, right? And that's one of the really, really cool things about quaternions. There are lots of really cool things about them. I mean, they're great. I love them. But this is a really cool one too. And it's just the fact that it makes it easy to do either of the things that we want to do. So there you go, and if you have any questions on any of this stuff, this is all going to be posted, and there'll be follow-up and everything on the forums at www.mollyrocket.com/forums, or you can just go there and there's a link to forums, and it's in the Tech Notes forum where this stuff is. So there you go.